5, 4, 3, 2, 1. Start, sir.
Good evening. Good evening to friends from India, and good morning to our friends and faculty from the West, from US. So we are now starting session 3 of our research methodology. Good evening to friends from India. And in first session, we learned how to frame a question, and we also learned how to design a study. In the second session, we talked about various ways to capture your data. We also talked about how to design a randomized controlled trial. Now we have a very interesting session 3. Dr. Reddy will talk to us about how to do research in a resource-constrained setting. So let me first introduce our faculty for the session. Dr. Rakesh Agarwal will not be able to join us today. He's got another engagement, but Professor Paul Thuluvath is here. Professor Thuluvath, we know, is Director, Institute of Digestive Health and Liver Diseases in Mercy Medical Center, Baltimore. He's also Professor of Medicine in the University of Maryland School of Medicine in Baltimore. Professor Thuluvath is a course director, and this session has been possible because of his efforts and, of course, Kaushal and Dr. Rakesh Agarwal's efforts. We have 3 moderators. I'll be moderating one of the sessions, and we have Harshad. Harshad is a dear friend. Harshad is a professor in gastroenterology and head of department at St. John's Medical College in Bangalore. The good part is, in addition to his DM in gastroenterology, Harshad also has done his diploma in child healthcare. So he takes care of both adult and child healthcare diseases. But the biggest claim to fame he has is his work in drug-induced liver injury. So I would say the single most maximum number of daily articles are from Harshad's institute, published by Harshad. And we also have Madhumita Prem Kumar with us. Dr. Madhumita is an assistant professor in PGI, Chandigarh. She's been trained in Delhi in MAMC and ILBS. She did her hepatology from there. But she has one attribute which none of us has. She's been to Antarctica for 1 year. Can you believe it? 1 year. She was a medical officer in a scientific expedition to Antarctica. Maybe we can hear from her what she learned from there. May I invite Professor Thuluvath to say a few words, and subsequently we can start the session.
Good evening, Manav. Thanks for the introduction. And I was thinking whether Raj and I should go to Antarctica to get out of this COVID. What do you think, Dr. Prem Kumar? That may be one place we may not have it. So I just want to thank Dr. Agarwal for co-directing this course, but almost all the heavy lifting is done by Kaushal. Raj and I helped from behind, found some speakers, but he did everything. So Kaushal, thank you again. And I will just hand it over to Dr. Wadhwan.
So Harshad, can I ask you to invite Dr. Reddy and introduce him, please?
Sure. So it's my pleasure to invite Dr. Rajendra Reddy, who is the Rumi Family President's Distinguished Professor of Medicine, Director of Hepatology, Viral Hepatitis, as well as Liver Transplantation, University of Pennsylvania. He has authored or co-authored over 500 peer-reviewed publications with H index of 101 on a spectrum of hepatobiliary topics. Most importantly, and this is very important, he is a recipient of the Distinguished Clinician Educator / Mentor Award at ASLD last year, that's 2019. And this is a citation that I really like about Dr. Reddy that was presented at ASLD. He is always filled with unbridled passion and enthusiasm. His influence and impact in clinical care integration and research and mentorship position him as an enduring role model for all of us. Thank you, Dr. Reddy, and we look forward to your talk.
Harshad, thanks very much for the generous introduction. Hello to everyone who's listening. I really miss visiting India and interacting with you all during these terrible times. It's really unfortunate, yet this is a great opportunity to learn. And I guess to share some thoughts on how we should conduct research. You'd have to pardon me if there's a bit of an overlap with other talks, but still I think there are certain points I want to make that hopefully you'll find helpful in your careers. But this is a time where we need to maybe rethink how we do our research as well because of this pandemic. And in fact, to that end, there's going to be a document soon online on clinical research during the pandemic and beyond the pandemic. And then there are really going to be challenges, and there's going to be a need for innovations. What happened here? So I'm not able to move the slide. Anyone?
You can just double click your pad, sir. That might work.
Okay.
Yeah.
Okay, yeah. So these are my disclosures. And well, it's not moving again. Oh, there you go. So we want to ask ourselves, why do you want to do research? You know, because people want to do research, but they need to have a full, good vision. I guess more often it's to further academic career. You know, publications are essential for promotion. You want to make some academic advancements, and then recognition is important, and you want to distinguish yourself from the rest. There's intellectual curiosity. You want to develop scholarly skills. You want to make a contribution to science. And then, of course, there is the benefit of getting funding, which may help not only in a current project, but projects down the road as well. Certainly, you don't want to do this because you want to impress your parents or your siblings or your peers. I mean, that's not the right reason to do research. You really have to have a commitment to it, and it could be a combination of all these factors. There you go. All right, so the types of research and where do you do them? The one is clinical research, translational research, and basic science research. And this could be done within your institution or outside by collaboration with a variety of other investigators and institutions. So start off with baby steps. I always say you have to learn to walk before you run. You just don't want to get into a race. Start off with a simple basic steps. So you want to have a clinical idea or observation. That is even the first step before you even think of any funding. And I've given an example of patients with cirrhosis being infrequently on aspirin or statins. Do they provide benefit in decreasing rates of complications? You could do a PubMed search on a particular topic, and then and there's an example here. One of my junior colleagues said, well, I really want to assess the role of direct-acting oral anticoagulants in portal vein thrombosis. I said, well, let's first look at the literature and before we kind of address the question. So you looked at the literature and actually wrote a very nice review article in Seminars on Liver Disease. And then now we've taken this forward with a database. We've created a REDCap database, and we're going to collect data around the country to see the patterns of thrombotic disorders, the interventions that are being used, the outcomes. And then I guess that's an example of trying to figure out what the unknowns are, and then you could then proceed forward. Now, funds could be through various sources: personal funds, school funds, professional societies, foundations, etc. But sometimes it is it's just your time that is the main source of "quote-unquote" fund. So, time commitment. Who's paying? If you look at the resources, that you're paying for it, the institution is paying for it, are there other funding sources, industry, national institution, foundations? And then databases. Are you going to use your own database, create a database and use it? Are there institutional databases that are already in existence? And are there databases in the public domains that you need to look at? So let's look at some examples of unfunded research. And before that, you want to have a stepwise plan. You need to identify a mentor who can make the commitment. That's very critical, because if a mentor says, okay, I will help you out here, but you send him a proposal and you get a response back 4 weeks later, that's not a good mentor. Your mentor is someone who's got to get it back in 2 days. That's the way it works from my end. That's the way my Saturday and Sunday goes. I got about 3 mentee projects that I got to overlook this weekend. So and then the mentor's role is to guide you in the hypothesis generation, the aims of the study, the plan, and the feasibility. Sometimes we have great ideas, and then you realize, hey, it's not even feasible to do this study. So you got to figure that out up front. Then you need data collection, and it could be prospective, retrospective. Then you have to have an analysis plan that eventually should lead to a full paper, not presentation. I have a simple dictum. When the ratio of abstracts to publications is infinity, there's a problem. You should really have at least a 50%. I would like an 80% transition track record from abstract to publication. So something that you need to keep in mind. If you're not going to publish a paper and just leave it at a poster stage or a oral presentation stage, that's just not good enough. So what is the largest clinical research commitment that one needs to make? It's individual time. And then the time is the easiest research cost to donate. You may not have dollars, but you certainly, or rupees, and you would certainly have the time. So you need to make that commitment. And then you have to understand that various people at various stages in their careers are challenged to provide their time. So and also you have to recognize that at various stages there is more and more time commitment required. So if you're the principal investigator, there's a lot more time involved. A sub-investigator, relatively less. Trainee, less. So as you further you go down, it's a less cost. But then they're not going to have the experience that a principal investigator or a mentor is going to have. So something that you need to keep in mind. So least experienced members of research teams should perform data entry. So you really need to assemble a good study team. About 2 to 4 people work best. You want to avoid redundancy. They have to have individual roles. You need to have a project outline, institutional review board submission if you need that. You need a database. You need to create it, perhaps. As we created one recently for the thrombotic episodes in patients with cirrhosis or independent of cirrhosis. And it didn't really take a whole lot of time. So something you need to work on. Biostatistics, either you should be trained or you need to partner with someone who can help you with biostatistics. And then scientific writing is critical. I mean, that is, again, an area where a mentor can help you. People write a whole storybook. A paper is not meant to be a storybook. It is key findings, a bit of background, data, a presentation, and then lastly, the discussion should be around the key elements of your work, not again a whole storybook. So now, and the key thing is this unfunded research is to be done off duty hours. So you do have a day job, like. I don't have a day job this weekend, but that's where I spend my time going over my research and papers. If you had asked me yesterday, Friday, at about 2 o'clock, I said, look at my paper. There's no way I would do that. So, or could do that. So you have to keep in mind you have a day job, and then you do your unfunded research outside of your day job. It's a sacrifice. If you want to succeed, you have to make a sacrifice. Now, retrospective studies are cheaper, but they are likely to have limitations regarding missing data, confounding variables, and also a database is worth what data is put in there and who puts in there. So something that you need to keep in mind. Prospective is more expensive, and more importantly, it's time consuming. But it allows for more control of data acquisition and scientific exploration. So as a starter, you may start off with a retrospective study while you are setting up your prospective study, because prospective study, it takes time to mature. So something that you need to keep in mind. So at least in the US, there are several databases that are commonly used. One that we use is a REDCap for data entry, and then other databases that are in existence are in the Veterans Administration System, then there are transplant databases, and then there's the National Center for Health Statistics database. These are a few examples. So we need to kind of think as to what kind of database could I have access to in India? And I apologize, I'm not familiar with all the databases that one may have access to in India, and that should be brought out in the discussion. But at least, you can create your own database on a particular topic, maybe partner with a couple of other institutions to have a more robust database. Now, REDCap, it stands for Research Electronic Data Capture Database. It's a web-based application. It's developed by Vanderbilt University. It's secure. It uses surveys and forms as research capture tools. And we've used this in a variety of studies. Right now, you've heard of NACCEL, some of you at least, the North American Consortium for Study for End-Stage Liver Disease is entirely REDCap based. And I'll present a study publication that we had recently that also came out from REDCap database. Now, what is important for us is that institutions need an agreement with Vanderbilt. But what I highlighted here is that there are apparently at least 80 similar databases focusing on clinical research data capture. And it's only a matter of time before more and more of these become ubiquitously available for people in other parts of the world to get access and then use. There are some hiccups there with these other databases. They may not be designed for clinical research, but it's only a matter of time before one really sees these come out to be ubiquitously available for all investigators. Now, there's some pros and cons of REDCap. For us, it's, as I said, its access is free. Previous knowledge of programming isn't necessary. It's more secure than Microsoft Access and Access. It's HIPAA compliant because it's a very sensitive issue. You have backups and easy to export data. The cons, while there are some, the one I highlighted is the integrity of the data. And it's true of any database. You look at UNOS, transplant database, scientific registry for transplant recipients database. Data is as good as the people who enter the data. So something you need to really be aware of. So it's not as granular as a database that you might create. What is happening, though, is in some of these databases, we are able to electronically dump our data, a site's data into a central database. So as time goes by, there are going to be relatively fewer errors or missingness. Now, statistical knowledge. There are programs that provide free statistical this education, something you need to be aware of. You don't need to take a class necessarily where you pay. So there are free online videos to learn the coding skills necessary for this particular software. So there are statistical programs that you can use to get some online education. I want to give you a couple of examples of investigator-initiated and funded research so that hopefully this will motivate you to pursue this path. So one of my junior colleagues wanted to study the role of ursodeoxycholic acid in hepatic sarcoidosis. And they said, well, why don't you first look at the literature and then see what the literature has to say. And then he and one of the medical residents did a literature search and came out with a review article in Seminars in Liver Disease. And that was the launching pad or the springboard to seek some funding. Mentee is Dr. Weinberg, and so he reached out to our Penn Clinical Research Fellowship Program. He got some salary support. He reached out to the American Association Study for Liver Diseases and got a pilot grant. He reached out to Excellence Bioscience to provide supplies and data analysis for a methacetine breath test. He started enrolling patients, and he's close to completing enrollment of a pilot study. So this is one way of doing it. And look at this. It started in August of 2018. And so we're 2 years out, and it's just about finished. So it takes time, but it can be done. Now, databases. There are several databases out there, but I want to just focus on one database. This is an industry-funded database called Target NASH. And there's several sites around the country that enroll. And something that culturally we need to perhaps think about for countries like India, because there is a lot of industry support, but maybe it could be channeled towards supporting databases. I know there's a lot of support for meetings, travel, other grants, but they potentially could support large databases. And then out of this, now it's mature enough to make observations. Again, I asked my junior colleague to put out a proposal on asking a particular question, and then he put out a proposal to the database steering committee. And he basically looked at lean Americans with the non-alcoholic fatty liver disease and looked at comorbidities compared to the overweight and obese North Americans. And he has a very nice publication in clinical gastroenterology and hepatology that is online now. So you could think of similar databases in India for conditions such as acute liver failure. One of my mentees did that in South America for acute liver failure, liver cancer. I know there's an ACLF database. A unique one would be liver disease in pregnancy. That would be phenomenal if someone were to come up with that. And Harsha, this is a phenomenal example of pursuing real life data. Gathering and making observations in drug-induced liver injury. So it can be done. So you need to have the commitment. Other examples of unfunded research. This is a great example. This happened recently. While we were shut down with this pandemic, we realized we had the RedCap database for NACSEL. So Jazz Bajaj and I started thinking and said, hey, listen, we really need to maybe make an observation in advanced cirrhotics. So 7 sites got together and looked at all cirrhotics who were hospitalized with and without COVID infection. And we also, the uniqueness of this was we identified a contemporaneous cohort of COVID-19 patients who without underlying liver disease. A lot of the papers that have been published are retrospective, what do you call not match studies and registry studies, etc. So this was a contemporaneously matched cohort study of 3 cohorts, and this has just been published in Gut, and we've matched by age and gender at a ratio of 1 to 2 or to 1 to 5, depending on how many COVID-19 alone cases there were in a particular institution. And here, what is interesting is that COVID-19 plus cirrhosis had similar mortality to cirrhosis alone. These are hospitalized cirrhotics, but the cirrhotic cohorts had a higher mortality than COVID-19 alone. And here are some of the clinical characteristics and hospital course characteristics. And what is important, I mean, there are lots of observations here, but if we were to look at mechanical ventilation, those who had COVID-19 alone or COVID-19 with cirrhosis was 39 and 38%. Those who had cirrhosis alone, low rate of mechanical ventilation, but they had cirrhosis-related events more common. So the message from this work is that mortality is high in cirrhosis patients with or without COVID-19. Without COVID-19, they die of cirrhosis-related complications. With COVID-19, they die of COVID-19-related complications, but still like a washout. And ultimately, the only thing that mattered in a multivariable analysis in all these cohorts that predicted mortality was Charlson's comorbidity index. So if you have a pure protoplasm, they don't do well. So lastly, I just want to talk about how you should think about a project. Medical residents come to me and my colleagues and say, listen, I want to do a research project. Yeah, so well, then we give them an idea, and then we say, listen, you got to come up with hypotheses and aims. Without that, it just can't move forward. You know, there's nothing like, let's look at this. What do you mean, look at this? What is the question you want to ask? So the question came up in the U.S. Some centers do not treat hepatitis C while they're awaiting liver transplant, because there is the opportunity for them to get hepatitis C infected organs. So we say we would treat them post-transplant. But are we doing the right thing? Maybe we are hurting them rather than helping them. So similarly, cancer patients on transplant list with hepatitis C, we don't treat them. We just say, let's treat them post-transplant because we believe that they have a chance of getting hepatitis C infected organs. So we generated a lot of hypotheses and then have specific aims. We want to see actually whether we're hurting them or helping them. So you need to, and then you need to have some sort of idea of the sample size. If you don't have the patients in your institution, you need to really think about adding other institutions. And the point of this is it's a medical resident. There's no funding. The person wants to advance academic career, and it's a free time that I'm providing. It's a free time the resident is providing. So something that should be kept in mind and be done. Lastly, I want to show one example of one of my mentees from Thailand, who came from Thailand, is self-funded, self-trained in statistics, and spent 2 years under my mentorship, and continues to work effectively in Thailand. He's done considerable scholarly work. And here are some examples where he collected data during the 2 years he was with me, and made observations. That highlighted ones are where he collected data. There's actually one terrific review he wrote on immune dysfunction and infections and cirrhosis, and the others are primarily reviews that he wrote while he was collecting data for other publications, and here as well. And so it can be done, and it is important that you take baby steps and then accomplish your goals in a nice scientific manner. So, a few thoughts at the end. Setting goals is the first step in turning the invisible into the visible. That's what an American author said. Tony Robbins. Plan out your research path. Most important is to have a mentor who has a time commitment, and that's very critical. Life, this is a mantra I teach my kids to this day and my mentees. Life is a marathon, not a sprint. It really happens over time. There are several pathways for clinical research, and funding of the long run is available. You have to develop in-house and multi-center databases, use existing databases, make preliminary observations, and then establish a track record. Once you have a track record, people will say, this is a person I want to make my investment in. And then, he's a go-getter. He will get it done. And then this is important. No one does charity. There's no free ride, no free lunch. There are expectations for the support provided. Even I, as a mentor, if I'm making the time commitment, I expect my mentee to deliver. Otherwise, I walk away. I said, listen, it's not worth my time investing in this person. So a fair number of people come, they start, and then they putter, and then they stop, and I said, I cut my losses and move on. As a mentee, you want to prove yourself that you're worthy of an investment, and that's what I've just highlighted. So with that, I'll end. Thank you very much for your attention, and I will be glad to take questions later on. Thank you.
So Manav, as we discussed, we'll have the questions and answer at the end of the session.
Perfect. But I'll request all the attendees to keep on posting their questions as and when they think about it, so that we can take all the questions at the end. Thank you, Dr. Reddy, for such a lucid and simple way to go about capturing data, doing research, and how to go about it. Can I request Dr. Madhumita to introduce the next speaker?
Okay, the next topic of discussion is going to be hypothesis testing and research methodology. And our speaker is Professor Saurav Datta, who is Professor of Pediatric Medicine at PGI Chandigarh. He's also Adjunct Professor of McMaster University, Canada. And he's a pediatrician who has special interest in research methodology and has worked extensively on neonatal sepsis, probiotics. And he's here to elucidate how to test the hypothesis today. So over to you, Professor Saurav.
Hello, good evening, everybody. I hope I'm audible to everybody.
Yes, you are, sir.
Thank you. I'm indeed honored and privileged to have been invited to deliver this talk on hypothesis testing. I'm particularly thankful to Dr. Kaushal Madan for this opportunity. As you have heard, I'm an odd man out. I'm not really a gastroenterologist or a hepatologist, and I belong to a slightly different universe. But the principles of hypothesis testing and research methodology are common to all branches of medicine and, in fact, to science as a whole. So when we are talking about hypothesis testing, what exactly are we trying to do? In most cases in hypothesis testing, we are trying to find an association between two variables. And in our day-to-day life, we are constantly at a subconscious level trying to make associations and doing hypothesis testing. We are making associations between whether China is getting close to Iran, whether there's an association between a certain politician and another politician in Rajasthan, and so on and so forth. So we are constantly making associations. So how do you judge an association? You judge an association primarily by three methods. The first is by either accepting or rejecting an association. That means a yes or no situation, where you are rejecting or accepting what is known as a null hypothesis, and I'll be coming to that shortly. where at the end of the study, you're basically dealing with p-values that fall on either side of the magic figure of 0.05. The second method is to estimate the strength of the association. That means we are not just satisfied with accepting or rejecting a null hypothesis, but we're going one step forward and asking how much more risk is there in one group versus another group. And that is usually expressed through relative risks, odds ratios, risk differences, or mean differences, depending on the type of variable one is dealing with. And lastly, going even one more step further, estimating the precision of the strength of the association. That means within what range of values is the relative risk or odds ratio or whatever likely to be 95% of the times. So here we are dealing with 95% confidence intervals of relative risks, odds ratios, and so on and so forth. Well, in today's talk, I will be concentrating primarily on hypothesis testing, that is, accepting or rejecting a null hypothesis and the errors involved in that. Now, let's take a motivating example. If we have a hypothesis, for example, Tamiflu, which is the brand name for oseltamivir, the antiviral, the Tamiflu has lower mortality than placebo in patients with swine flu. Suppose this is our hypothesis. So what are we trying to do? We are trying to prove an association between the Tamiflu group and a lower risk of dying compared to the placebo group. To do that, we assume that there is no association, which is the null hypothesis. So epidemiologists have this peculiar roundabout way of trying to prove things. So they want to prove something, they first assume exactly the opposite and then try to disprove it. So the null hypothesis would be that Tamiflu and placebo have exactly equal mortality in swine flu. There is no difference between the two. And then we try to disprove the null hypothesis, that is, we try to disprove that Tamiflu and placebo have equal mortality in swine flu. And having rejected the null hypothesis, in which case we will be landing up with a p-value of less than 0.05, we are left with two alternate hypotheses in different directions. These are that Tamiflu has less mortality than placebo, or that placebo has less mortality than Tamiflu. And it is usually the data that tells us which of these two alternate hypotheses are true. So moving on, we humans have no way of knowing for certain whether Tamiflu is equal to placebo, or whether Tamiflu is better than placebo, or Tamiflu is worse than placebo, because we have no way of enrolling the entire universe in any study, the entire human population, and doing the study to come to a definite answer. And even if we could enroll the entire human population, we would never have been able to enroll the human populations that are yet to exist, yet to be born, and those who have already died. So there's simply no way in which we will ever get to know the absolute truth. So let us, for a moment, for the sake of argument, assume that there is a definite truth and only God knows the truth. Now, I don't want to get into arguments with believers and non-believers, but just for the sake of simplicity, let us assume that there is a definite truth about everything, whether Tamiflu is better than placebo or not, or whether lamivudine is better than placebo or not, or whatever, and only God knows the truth. Now, I request you to focus your attention at the bottom of the slide. I'm going to be showing you a horizontal line, which is the line of risk difference. That means the difference between the risk of death in the Tamiflu and the placebo arms. Risk of death in Tamiflu minus risk in placebo, so risk difference. And because it's an arithmetic figure, it extends from minus infinity to plus infinity theoretically, and the null value is risk difference equal to 0. That is when the risk of death is identical in the Tamiflu and placebo arms. It gives the null value of RD equal to 0. Now, even if the null hypothesis were true, that means there is no difference between Tamiflu and placebo. If we were to conduct innumerable studies comparing Tamiflu and placebo, their risk differences would fall just above or below the value of 0 simply by random chance. I mean, that's common sense. You won't expect every study that you do, even if they were identical, to faithfully provide you risk differences that are equal to 0. So they will be, above and below 0 just by a random chance. And it so happens that if we were to plot the risk differences of all these studies, assuming no difference between Tamiflu and placebo, the risk differences would have a normal distribution around the central value of 0. So risk difference is less than zero would mean that Tamiflu is better than placebo. That means you're getting negative values. The risk of dying is less in the Tamiflu arm. Risk difference more than zero. That means Tamiflu is worse than placebo. You're getting positive values. That means the risk difference in the Tamiflu arm is more than placebo. So far, so good. Now, a risk difference equal to zero means exactly equal risks in the Tamiflu and placebo arm, which is almost impossible to achieve. And it would be absurd to conclude that the slightest deviation from risk difference equal to zero means that either Tamiflu is better than placebo or Tamiflu is worse than placebo. So you have to give some flexibility, but then it is equally absurd to conclude that no matter how far the risk difference in a study deviates from zero, no matter how extreme the value is, the difference can always be ascribed to random chance. That means it is just by chance that it has become different than zero. So these mutually contradictory statements have to be resolved in some manner. And to do that, we have to draw a line somewhere, both literally and figuratively. So what we do is we put up limits. Say, for instance, from plus 18% on the one side to minus 18% on the other side, near both ends of the curves. So remember, we are talking about the risk difference in percent. So the percent of patients dying in Tamiflu minus the percent of patients dying in the placebo arm. So that 18% is, that's what we are referring to. And we say that, look, hold on. Only if the risk difference is beyond those limits will we conclude that Tamiflu is better than placebo or that Tamiflu is worse than placebo, in which case we will be rejecting the null hypothesis. So that means although we are still sitting on this blue curve, if it goes beyond certain limits, we'll say, okay, no, we can't accept random chance any longer as an explanation. Beyond that, we're rejecting the null hypothesis. Now, why on both sides? Because it's equally important to know whether Tamiflu is beneficial or harmful. And by convention, we want only 5% of the area under this blue curve to lie beyond these limits that we have put up. And that is being shown in the form of a dotted region. So the two dotted regions together should add up to 5%. So the area in each of these dotted parts is 2.5% of the total. The sum of the dotted areas is 5%, and that is known as the type 1 error or alpha error. Each side, the dotted area is alpha by 2 or 2.5%. So in these dotted areas, there is still, if there's just a 5% chance of wrongly rejecting the null hypothesis. That means it could still be compatible with the null hypothesis, but there's just a 5% chance of that happening. So as I said before, risk difference values of less than this negative value, that means less than 18%, more negative than 18% means that the Tamiflu is better than placebo. Risk differences greater than that positive value, more than 18% means that Tamiflu is worse than placebo. If it is anywhere between minus 18 to plus 18%, the middle part, we say that it is compatible with the null hypothesis. There is no difference between Tamiflu and placebo in this region. Okay. Now, these differences on either side of the null value that we have chosen, beyond which we consider the risk difference to be truly significant, should ideally be the desired effect size. That means the amount of difference between Tamiflu and placebo that would make you change your clinical practice, the desired effect size. And that comes by expert consensus. There is no magic figure. For different situations, different contexts, the desired effect size would be different. Okay, but supposing the truth is that Tamiflu is indeed better than placebo and that the real risk difference in the universe is minus 30%. That is the actual truth. That means that in the universe, it is the alternate hypothesis which is actually true. But if many studies were conducted, assuming the true risk difference to be minus 30%, they too will have risk differences above or below the central value of minus 30% simply by random chance. Just like how we had seen with the blue curve around the risk difference of 0 in case the null hypothesis was true. So the risk differences of all studies compatible with the alternate hypothesis that Tamiflu is better than placebo would fall in the gray curve with a normal distribution. minus 30, and on either side of minus 30, you're getting a normal distribution. Okay. Now note that these two curves overlap, the gray curve and the blue curve, the alternate hypothesis curve and the null hypothesis curve. But since we decided that this would be our cutoff for assuming that Tamiflu is better than placebo, now if we end up getting a risk difference to the right side of the cutoff, and if it is the gray curve which is actually true, that means the alternate hypothesis is true, we will commit the error of wrongly concluding that the null hypothesis is true. So what do I mean by that? Now, I don't know whether you can all see my cursor, but if you can imagine that you are sitting somewhere on the right side of this minus 18 vertical line, then, and you are part of the gray curve, then you are likely to conclude that the null hypothesis is true, because we had already decided that anything from between minus 18 to plus 18% is considered to be null hypothesis is true. So that means we would commit an error. And this hatched part of that gray curve is called the beta error, and or the type 2 error, and we try to limit it to just 10 to 20%, max 20% of the area under the curve. So putting it all together. So you can see the horizontal line at the bottom. If the null hypothesis is true, it is 0% difference. If the alternate hypothesis is true, minus 30% difference. So for a desired clinically important effect size, say plus or minus 18% is our desired effect size, we must recruit a sufficiently large sample size, which in turn determines the sizes of these imaginary curves through a complex process known as standard error. I don't want to get into that. But basically, the shape of these curves changes depends upon the sample size, and we'll come to that later in the talk. We must recruit a sufficiently large sample size such that in case the truth is that Tamiflu is no better than placebo, we don't incur more than a 5% risk of wrongly concluding that Tamiflu is significantly better or worse than placebo. And just in case the truth is that Tamiflu is actually better than placebo, we don't incur more than a 20% risk of wrongly concluding the reverse. That is, Tamiflu is same as placebo, identical to placebo, or there is no difference between Tamiflu and placebo. So the first is the alpha error, wrongly concluding that Tamiflu is better or worse. And the second is beta error, wrongly concluding that there is no difference between Tamiflu and placebo, whereas actually there is a difference. Okay, moving on. So what is p-value, and where does that come in this whole scheme of things? So p is just a short form for probability. So p-value is the probability of an observed difference, or in other words, an association occurring purely by random chance. So let's just try and demystify the p-value. So you're still dealing with this research question. Are mortality rates with Tamiflu and placebo different? Now look at this table. On the left-hand side, you have the risk of dying in the Tamiflu arm and the placebo arm. And I'm not telling you what the sample sizes are right now. We'll populate the sample sizes a little later. The third column is the risk difference between the two arms. The fourth column is something that the computer calculates for us using certain formulae. What is the probability that the difference that you're seeing is due to random chance? And from that, we are converting it into the p-value. Now, each of these rows that you're seeing filled with numbers represents a different study. So we are going to go study by study from top to bottom. So imagine the top study. The risk of dying is 50% in both the Tamiflu and placebo arms. The risk difference is 0. Since there is no difference, the probability that the difference is due to chance is not applicable, and therefore no p-value can be calculated. In the second study, note that the risk of dying in the Tamiflu arm is a smidge less than what it is in the placebo arm. It's 49% versus 50%. So the risk difference is minus 1%. The computer, using some formulae in the background, calculates that the probability that this difference is just due to random chance is 91.4%. And we just shift the decimal places to make it the p-value, that is 0.914. So that means if someone tells you that the p-value in a study is 0.914, what they're trying to say in simple English is that the probability that the difference that you have seen has occurred due to random chance is 91.4%. Unfortunately, because of using decimal places and because of converting the word probability into p, there's a certain aura about p-values. But what it means in plain English is very simple. It means there is a 91.4% probability that the difference that you saw was due to random chance. Now let's go to the third study. Now Tamiflu risk has dropped to 40%. So now the risk difference is 10%. The computer calculates that there is a 27.9% probability that this difference could have occurred due to random chance. So the p-value is now 0.279. Making the difference wider, Tamiflu 33% versus placebo 50%. There's a 17% risk difference. Probability that difference is due to chance is 6.3%. P-value becomes 0.063. 0.063 means 6.3% probability that difference is due to chance. When you drop the percentages a little more from 33 to 32%, minus 18% difference, 4.8% is the probability to chance. The p-value is 0.048. And so on. The p-values keep becoming smaller and smaller till finally the last study at the bottom, where Tamiflu has only 5%, the huge risk difference, 45%. But still, there is some probability that the difference is due to chance. So there are a whole lot of zeros and then a 1. And then when you shift the decimal places, 2 more zeros than what you already have, and a 1 is the p-value. Telling us that the play of chance can never be excluded. It never touches 0. The p-value cannot become 0, because no matter how extreme the difference, no matter how eye-popping the difference that you're seeing, there is always a minuscule probability that it could have occurred due to random chance. Now, if we keep saying that everything is due to random chance, we will be paralyzed. We won't be able to take any action. So therefore, it has been decided to draw a line somewhere. And that somewhere happens to be the 5% mark. So it has by convention been decided that once the probability that the difference is due to chance drops to less than 5%, chance as an explanation will be rejected. We will reject the null hypothesis and we will assume it to be a true difference between the two groups. And that's where your p-value of 0.05 comes. Now, from where and who made this cutoff of 5% of 0.05? It comes as a shock to most people to know that it's purely arbitrary. And it's probably related to the fact that we Homo sapiens evolved with 5 fingers in each hand. There's nothing more to it. And had we evolved like these people with 6 fingers in each hand, today we would have all been getting excited over p-values of less than 0.06. So what I'm trying to say is that not every p-value which is less than 0.05 is important, is of clinical significance. And not every p-value that has fallen short of that magic figure, which is hovering somewhere between 0.05 and 0.1, doesn't mean that they all need to be dismissed or poo-pooed. They could still mean important clinical differences. Now, how does the computer make these estimates of probability of random chance? To understand that, I'm going to take a very simple example plucked out of daily life. Now, I'm sure all of you have played Ludo at some point of time in the other in your lives. So let's imagine I'm playing a game of Ludo with my friends. And I want to test the hypothesis whether there's an association between my wishing for a 6 and the dice actually rolling a 6. So what I do is, I first frame a null hypothesis. I say there is no association between my asking for a 6 and the dice rolling a 6. And to test the null hypothesis, I ask for a 6 and I roll the dice. And to my astonishment, I actually get a 6. So the probability that the dice rolls exactly what I'd asked for by random chance is, and I'm sure all of you can calculate that, it is 1 by 6. Or in other words, 16.67%. And if I make it a decimal, it is 0.17. Okay. To test it further, I roll 2 dice and ask for a 6 on both occasions. And I actually get a 6 on both. So the probability that the dice twice rolls exactly what I had asked for by random chance is 1 by 6 multiplied by 1 by 6. That's 1 by 36. So that's 2.78%. Or 0.028. So there you go. There's no rocket science behind calculating p-values. We have ourselves calculated the p-value of a dice throw. A 6 rolled 1 has a p-value of 0.17. That means that is the probability that it could have occurred by random chance. Rolling it twice in succession is 0.028. We've already recrossed 0.05. And that's what the computer is basically doing in the background of all the calculations. Now, just revisiting the p-value on this table. Now, I told you I left the sample size column blank. So it so happens that only when you recruit 58 subjects in both arms, do you end up getting these figures. That means with an 18% difference, you get a p-value of 0.048. That means there is only a 4.8% probability that an 18% difference between the two groups could have occurred just by random chance. So if 18% was your target, your desired effect size, you would have had to recruit 58 in both arms to ensure that you get a p-value of less than 0.05 at the end of your study. So what is the effect of sample size on the effect size and statistical significance? Now let's look at this graph. So you have your familiar null value RD equal to 0 at the bottom. Now supposing instead of taking 58 per group, had we taken sample size of 30 per group, then the curve of all the studies resembling our study, the risk differences that they would have had for forming a normal curve, as I said right in the beginning, would have looked something like this, very broad and short, because our sample size is less. And you can see now that that dotted part, the 2.5% of the area under the curve, where we want our desired effect size to lie, is actually quite far away from the desired effect size. So the desired effect size of minus 18% has still a long way to go to reach the place where it would be considered to be statistically significant. So this sample size would end up having a p-value which is non-significant. Let's increase the sample size. If we take a sample size of 45 per group, the desired effect size line has now shifted a little closer to the 2.5% hatched part of the curve. And it is only when a sample size of 58 per group is reached that our minus 18% now starts falling at the boundary zone of the dotted part, which is the alpha error part of the curve, 2.5% on either side. And if the sample size crosses 58 per group, then of course, the sample size is actually too much to pick up a minus 18% difference. So p-values and the two curves. So first we fix our desired effect size, as I told you before, 18 plus or minus 18%, and you're familiar with the rest of this graph. So a sample size of 58 will give us curves of sufficient height such that if the null hypothesis is true and our study shows a risk difference of greater than minus 18% on one side and plus 18% on the other side, there is only a 5% probability of wrongly concluding that Tamiflu is better or worse than placebo. And if the alternate hypothesis is true, that means risk difference is indeed more negative than 18%, there will be only a 20% probability of wrongly concluding that there is actually no difference between Tamiflu and placebo, that they are similar. And that's basically, again, the type 1 and the type 2 errors that I had mentioned earlier. So at the end of the study, if the risk difference falls in any one of these dotted areas, the p-value would be less than less than 5%, that is less than 0.05. So just putting the whole thing graphically once more. So here's your null hypothesis curve. If the risk difference is minus 1%, we had calculated the p-value was 0.914. That means there is a 91.4% probability here that the difference that you saw was just by random chance. When you widen the difference, it's minus 10%, the p-value becomes 0.279. When it is minus 17%, it is 0.063. That means it's just falling short of what we call statistical significance. It is when the risk difference becomes minus 18% that the p-value jumps over that 0.05 line and now becomes 0.048, enters this dotted part. And of course, when it is a very extreme difference, a 30% difference, the p-value is very significant, 0.0012, right, sitting right at the left extreme of this slide. So, and this is when you have a sample size of 58 per group. So the take-home messages are that associations could be determined by either accepting or rejecting the null hypothesis, that means p-value of less than 0.05 or more than 0.05, or calculating 95% confidence intervals of the strength of the association, which I have not covered because it's not directly related to accepting or rejecting a hypothesis. Null hypothesis assumes that there is no association to begin with. P-value is the probability that the observed association is due to random chance. The p-value cutoff of 0.05 is only a convention. There is nothing sacred about the figure of 0.05. Alpha error is the probability of wrongly concluding that the alternate hypothesis is true, and beta error is the probability of wrongly concluding that the null hypothesis is true. A sample size calculation is basically required to ensure that there are enough subjects available to demonstrate an association given a desired effect size and given an assumed alpha error and beta error, which by convention have been fixed at 5% and 20% respectively. Thank you very much. I'll be happy to take questions at the end of the session.
Thank you, Dr. Saurabh. So we are quite clear how to test our hypothesis. We'll probably take up the values of 0.05 and the beta levels of 90% or 80% later on in the discussion. And how do you want to titrate them according to the type of study you're doing, whether it's an interventional trial or some other thing. So we'll probably take that up later on. Let's move on to the third talk here. Now, it's my pleasure to invite Professor Usha Datta to talk to us about use of statistical test. She'll give us a practical guide for clinicians. Professor Usha Datta is a professor in gastroenterology in PGI. She's also a governing council member of INASL, and she has a very keen interest in statistics. Actually, I think Saurabh and Usha, they hold these research methodology workshops quite often for a lot of us students and other people. Thank you, Dr. Usha.
Thank you, Kaushal, and thank you, Manav. Thanks for all the effort you have put in organizing these sessions amidst all this COVID pandemic. So what I have done is I've kept this extremely simple. Am I audible to everybody?
Yes, you're audible, ma'am.
Okay. So what I would be discussing on approach to statistical test, a practical guide for clinicians. It's a very simple lecture focusing on the basics so that anybody after this should be able to decide which test to apply. So I'll just briefly say what is statistics, how to manage your data, which test to choose, how to interpret, how to present the results, and some terms like odds ratio, risk difference, and number needed to treat. So the basic thing about statistics is it is a set of principles and procedures which are used for analyzing data. So you have the big N, that is the population, from which we draw a sample which is representative, random, and adequate. These are necessary to satisfy the assumptions that we make in statistics. And we draw a small sample. So as you realize, if you want to study all the diabetics in the world, it is just not possible. You would be studying only a small N out of it. This small N you closely observe and analyze. And in that is where you do your descriptive statistics of mean and standard deviation, median and IQR and counts. But using probability theories, we now extrapolate this results into the main population. So that is why if you do a study in diabetics in about 200 patients, and then you say, oh, we had a good confidence, narrow confidence interval, we have good reliable data, it's valid. Now the whole world can try that drug. And that is how we are using our probability to extrapolate it from our sample to the whole population. So it has essential steps like the case report form, which is converted into a spreadsheet like Excel. I use SPSS, but there are various statistical programs. You put it into any of the statistical programs and you get a p-value. So the data is usually arranged in the form of columns will have the various variables and the rows have patients. The titles have to be self-explanatory because sometimes you accumulate data and revisit it after some time. By that time, you have forgotten what each column meant. So, and the structure, pre-structured codings, especially for ordinal variable, what is 1, 2, and 3, and 4? Is it mild to severe or it's severe to mild? And random checks, especially for authenticity of data. Whenever your student comes up with the thing, I usually cross-check with the CRF and also hospital data so that I know that the data which is there on the database which is in front of me is authentic. And we have to ensure data safety. Otherwise, sometimes the computer crashes at the last minute. The data is entered across, as I said, the serial numbers here. So apart from the computer serial number, have your own serial number so that when you sort, you can come back to this. You have the names. The CR number is the unique number. And then you have put them as cases or controls. So cases, whatever is there on the title remains 1. Whatever is absence of the title variable becomes 0. And you have the age in the same units, especially when you have children and adults in the study. And then we have the gender. It's better to code them as male as 1 and 0. So 1 means male and 0 means female, rather than code it as 1 and 2 and later be confused 1 was male or 2 was male. So there are many statistical programs. You have to familiarize yourself with one. SAS, StatsView, Minitab, R are all there, where you quite often write your own coding. But I use SPSS, which I find it effective in most of the level of statistics that we do. And GraphPad is available online for small kind of calculations. So let us take a clinical scenario. In this clinical scenario, I have weaved in how to choose a statistical test. So our study question is obesity associated with hypertriglyceridemia? Just a very simple question. So our objective is to study the association between body weight and triglyceride. Then is there a relationship between triglyceride and cholesterol? We just want to explore. And whether drug A given, does it result in more reduction in triglyceride level compared to placebo? So just a simple study design. We have 100 obese people, 100 overweight, 100 normal. We study their weight at baseline, their triglyceride cholesterol level, and a radiologist does assess for fatty liver, whether it's present or absent, and then he grades it as mild, moderate, severe, or 0, 1, 2, 3, 4. And then you give a drug versus an identical placebo in an RCT design. And you reassess after 4 weeks whether the weight reduced, whether the triglycerides went down, whether the cholesterol went down, and whether the fatty liver resolved at 4 weeks. So this is our hypothesis and this is our study design. So this is what is the data we get. So we have 3 groups: obese 100 patients. Their mean weight was 100, which is understandably higher than the overweight 100, more than the control. So these are hypothetical data. So don't look into the data for any answers. Triglycerides are higher in the obese group compared to the overweight compared to the controls. Similarly, cholesterol is also higher. And if you see, fatty liver is more often in the obese compared to the overweight compared to the controls. So when we also look at the grade of fatty livers, that is 0, 1, 2, 3, 4, we see that it is in the obese, you more often have higher grades of fatty liver. Notice this orange blocks because these have very wide standard deviation. So this means most likely this data may not be normally distributed. This is something which we have to note. In contrast, you see here that the standard deviation is very small. So after treatment, you get this data. There's some reduction in weight in all the arms. There's reduction in triglyceride, cholesterol, number of fatty livers have gone down. The grades of fatty liver has gone down. So you want to analyze this data. So which test to apply? So this is a difficult question for most people. So I have just simplified it. There are 5 key questions. The first question is what type of variable you want to analyze. Second is your data less than 30 in number or more than 30 in number? Is your continuous variable normally distributed or not? Are you analyzing 1 group data, 2 group data, or more than 2 groups data? Are the samples related or unrelated? So if you answer these 5 questions, you can decide which test you have to do, and I'll take you through each one of them. Now, type of variable. Variables are of 2 types, category or number. This is something which we have to first understand. Category is, say, male, female, either a person is male or a female. So it is a person belongs to 1 group. Whereas number is something like height, weight, or something which is actually quantified as a numerical variable. So it can be called categorical variable and numerical variable. The categorical variable can be yes, no, that is obese, not obese, male, female, response, no response. It can be more than 2 categories, that is polynomial. A person lives in Chandigarh or Ambala or Kurukshetra, so you want to classify city wise, and here there is no order within them. So that is more than 2 categories without an order, or you can have an order within them, like grade 1, 2, 3, 4 for fatty liver, grade 1 to 6 of cardiac murmurs. So that is an ordinal variable. The number can be a continuous number or it can be a discrete number. I'll come to both of them right now. So as I said, yes and no binary is obesity. A person is in the red circle or in the green circle. And then you have a city of residence, 4 or 5 different cities of residence. There is no order amidst them. Then you have the grade of fatty liver. You see all of them is blue color, but increasing order or decreasing order of severity. And then you have a height, weight, and BMI in the form of a scale. It can even have a decimal value. However, discrete is the total number of patients with high triglycerides. That means it has to be a discrete number. That can't be 4.5 or 8.5. It has to be a discrete number. So next is, what is the size of data? Usually large data are normal in distribution, they are robust, and they have assumptions are usually met, which we have for statistics. And more than 30 subjects if you have in a group, then you check for the distribution. If it is normally distributed, you apply normally distributed statistics for that. Or if it is not normally distributed, you apply the non-parametric statistics. But if it is less than 30, in general, it is a good idea to consider it as a skewed data and apply only non-parametric statistics. So the key thing to the second question is less than 30 or more than 30. The third question is the continuous variable normally distributed or not? So normally, how do you say? It's a very simple thing. Just draw a histogram and see whether it is forming a bell curve. This is just an eyeball kind of a test. Next is you can do a PP plot or a QQ plot. If all your red dots lie on the central green line, that means if most of it lies on that, that means it is having a normal distribution. There are 2 statistical tests, Kolmogorov-Smirnov test and Shapirov-Wilk test. If the p-value of this is more than 0.05, then it is normal. Now, how can we do these simple tests? Actually, in the SPSS, you just go and click 1 or 2 buttons and you will get this p-value. And if the p-value is less than 0.05, it is skewed data. So here you can see that in the height is 162 centimeters, standard deviation is very small, 8. And that is why your p-value here is nearly reaching 1. That means this is a normally distributed data. But whereas in this situation, you see 91 and a standard deviation of 22. So it's a wide dispersion and not homogeneous, and hence it is most likely a skewed data. Now, why do we worry about normality? Because most large physiological data are normally distributed. And the t-test which we are using, that is this red pink line as such, pink graph, this starts approximating the Z distribution. So the Z distribution is the blue line. But if the sample size is less than 30, you see the curve, it doesn't actually follow the Z curve and hence does not follow the T distribution, and hence we cannot use our standard t-test. So that is why the rough thumb rule of 30 sample size. Now, next thing is, as I said, how does the data spread? You look at the distribution. If it is normal, why are we so interested in knowing it's normal or skewed? The normal one, we use parametric statistics. For the skewed one, we use the non-parametric statistics. The classic type of that is the student t-test here, and it's the Mann-Whitney U-test here. Usually, these are the physiological parameters. We express it as mean and standard deviation and use a bar graph to show it. And in the skewed statistics, we use skewed distributions. We use small data sets whenever it's less than 30, ordinal variables. We use median IQR, and you use a box plot to show this data. So also all ordinal variables are analyzed as non-parametric. All small data sets are analyzed as non-parametric, as well as any data which shows that it is not normally distributed is analyzed as non-parametric. So this is a very essential point people have to note. So the choice of statistical test is based on a lot of assumptions of normality and randomness, and that is why we need to look at it. So next question number 4 is, how many groups are we studying? So the first thing you see is an obese group, that is the patients with who were obese. In that, we want to see the relationship of cholesterol and triglycerides. So within one group, you are studying 2 variables. So this is a one group study. Obese group versus the normal group. Here you are studying obesity versus triglyceride levels. So here it is 2 groups we are 2 independent groups we are looking at. And the third set is obese, overweight, and normal. So here we are looking at 3 groups. And when we want to do any analysis, so this is a 3-group situation. So this is the 4th question you have to answer. So the 5th question is, are these groups related in any ways or are they independent? So if we go back to this, see, the obese people have been drawn from the population, the overweight have been drawn from the population, the normal have been drawn from the population in an independent way. It is not that this obese patient dictated who will be the overweight drawn into the study or who will dictate who is the normal who is come into the study. So since there is no way by which you have actually linked these people at the time of drawing them in, they are independent samples. And ideally you have to draw them randomly, but because practicality does not allow it, so we use consecutive patients instead of random patients. And suppose for one obese patient I had taken a person whose age and gender matched. For each patient I have, say, a 50-year-old person who is having 50 kg or 80 kg and who is a male. I pick up from the normal population, I pick up somebody 50 plus minus 2 in age and 80 plus minus 2 in weight. You know, if I pick up a similar kind of situation from there, that's called matching. There I have to again use they're called related samples. So coming back to this, so related samples can be if you are drawing them with something, not drawing them independently, and or if it is before and after treatment in the same person, or right eye and left eye, because it is in the same person. On the right eye you're putting a drop, left eye you're putting another drop. So it is they are related and hence they will be analyzed separately. Twins will also be analyzed separately because there are a lot of genetic things which are going on similarly. And as I said, if you have a control who's particularly matched for that particular case, then again you will do analysis for matched samples. The unrelated ones, as I said, is obese group versus non-obese group chosen independently. So now we come to which test to use. I will just deal with 3 common categories, that categorical versus categorical, continuous versus continuous, and categorical versus continuous. So let us take an example. If I want to study the effect of obesity and versus high triglyceride levels. So here you see the triglyceride was a continuous variable. I have made it into a category, that is high versus low. So now this is also a categorical variable. This is also a categorical variable. And now if they are unrelated, that means they have independently come from the community, I use a simple chi-square test. Whereas if they are related, that means for every patient in the obese group, I had taken a matched person from the control group. They are somewhere related and they're not independently coming from the community. I will use a McNamara test. If there are 3 groups of like obese, overweight, and normal, and 3 groups I'm looking at those who had high triglyceride levels, then I use chi-square test again. Chi-square can be used for 3 into 2 tables, 3 into 3 tables, 4 into 4 tables. You can use that. So let us go with an example. Now we have obese people n equal to 100, controls n equal to 100, triglycerides 70% have high triglyceride here and 30% have normal triglyceride. In the control group it's 10% and 90%. So we have the 5 questions here. Both are categorical variables. Data is more than 30, that is n into 100, n into 100. Both of them, here there is no role of skewed distribution because here we are not interested in that. And these are 2 groups we are analyzing and they are not related because they have come independently. So we use the chi-square test. So now when we look at the same thing, obese, overweight, and control is a 3 into table, a 2 table. Again, it has more than 2 categories. All other things remaining same. Again, we are using chi-square test. Now, this is how the data looks like. In obese, you find that a large number of people are having high triglyceride compared to the control group. You see the graph itself tells you that something is happening. So there are more observed is more than the expected. And if we go to the next slide, you see 2 into 2 table, high triglyceride, normal triglyceride. This is how the table looks. If there is no relationship, I think i.e. the null hypothesis is true, then you should have equal people in all the arms. But now you see you should have equal people 50, 50, 50, 50 in all arms. But actually when you do the study, you actually get 70 here and a 30 here and a 10 here and a 90 here. So what you're observing is different than what you would have expected. I've just kept it extremely simple here. And thus, there is something happening, some association between obesity and triglyceride levels. So the chi-square test is basically looking at observed versus expected. Now this is the observed and this is the expected. Again, here is the observed, this is the expected. So it puts it into a formula. I will not go into that. And in simple terms, it is AD, this into this, divide is more than this into this. So 70 into 90 is more than 30 into 10 in a very big way. So most probably I expect a strongly positive chi-square. A high chi-square and a very low p-value. So if the chi-square is larger, the p-value becomes lesser and lesser, and then a null hypothesis is unlikely. It is not due to random chance that they're distributed in some way. That is why obesity seems to be related to increased triglyceride. So if p-value is less than 0.05, then we reject the null hypothesis and we say obesity is associated with high triglyceride. Please note this term, it is associated. It does not mean obesity is causing high triglyceride unless we satisfy the Bradford-Hill criteria. Right now, I cannot go into that. You can check it out. So then how do we interpret the chi-square table? Always we use two-sided value because we are using the alternate hypothesis is two-sided, meaning that obese people can have higher triglyceride or lower triglyceride. And then what we do is we look at the Pearson chi-square, p-value of 0.000, which basically means that p-value of 0.001. So this is ideal for samples which are more than 30 and 40 in number. If the sample size is small, then we have to do a continuity correction. In small samples, we use the continuity correction. It's called the Yates continuity correction. And if the cell size are very small and the expected amount in any cell is less than 5, so that is where we look here, expected count is less than 5, then we use a specific test called the Fisher's exact test. Again, this is a two-sided test which we use. These things are also available on GraphPad. So then how do we report? We say that the prevalence of high triglyceride levels in obese group was significantly higher than the control group. So significantly, we use the word only when the p-value is less than 0.05, and we represent the numerical data in this way so that the reader knows what exactly we are trying to say. So if you have to do this in SPSS, in another study which we had, case control versus vitamin D, you just go on clicking certain things and it's easy to go through it. Nowadays on the net, there are lots of teaching videos also. So you click chi-square, you get your value, and on that basis, you report it. Now we come to, once we have this 2x2 table, there's also these terms called odds ratio, risk ratio, and risk difference. So in order to understand this, all of you would love to eat a pizza. And describing binomial variables, so this is a slice of the pizza divided by the remainder of the pizza. When you do a slice of the pizza divided by the remainder of the pizza, it's odds. When you do slice of the pizza divided by the whole pizza, it is risk. So this is in essential terms. So that is what this is, a slice of the pizza. Slice of the pizza divided by the remainder is odds. Slice of the pizza divided by the whole is risk. So what is odds ratio? So in the obese group, slice of the pizza divided by the remainder, whole divided by slice of the pizza divided by the remainder in the normal group, that gives you the odds ratio. Similarly, slice of the pizza divided by the whole pizza and divided by the size of the pizza by the whole pizza, here is the risk ratio. So essentially, the numerator remains the same, but the denominator here is the remainder, denominator here is the whole. So obviously, this number will always be bigger than this number on either side of 1. So odds ratio will always tend to overestimate the effect size. Clinicians intuitively think of probability, that is incidence of event among a group, whereas gamblers and weather forecasters think of odds, chance of space, ace of spade versus chance of no spade, chance of rain versus no rain. So as I said, OR will always exaggerate the effect size, and the OR will tend towards the relative risk if the event rate is very small, because the remainder and the whole virtually become very similar in their numerical numbers. So interpretation of RR, if it is 1, that means there is no increased risk or decreased risk. If you go towards 2 and 5, it is associated with moderate risk and bigger risk. If it is on the 0.5, 0.2 and 0 here, then it is giving us protection. And if you notice from here, it is 0 to 1 and here it is 1 to infinity. So always this number will look very big and the protective RRs will look very small. So what is risk difference in NNT? Risk in the drug arm minus the risk in the control arm. Here it is minus. In the risk ratio, it is division. Here it is minus. So please note that. So risk can be also, risk is just a word which we use. It can be response rate in the drug arm says 80%, so it becomes 0.8. Response rate in the placebo arm is 30%, it becomes 0.3. So risk difference is 0.8 minus 0.3, 0.5. And 1 by risk difference becomes NNT, that is 1 by 0.5, it is 2. That means you have to treat 2 patients to expect response in 1. Smaller the NNT, the intervention is more efficacious. So that is in a nutshell, OR, RR and RD and NNT. Now we come to 2 continuous variables. So if continuous variables, 2 ones, you want to see, are they associated? You do correlations tests. If you see whether one variable affects the other variable, means it is somehow dictating the other variable, then you do regression. Third is if you see one variable is agreeing with the other variable, then you do the Bland-Altman plot. I'll give you an example of these two. Cholesterol and triglycerides can be associated with each other. As one increases, the other increases. So that is correlation. Affects, if the weight goes on increasing, the triglyceride levels may go on increasing. So that is, it may be regression. We are saying one thing is causing the other thing. And the third is, if you do triglyceride by 2 particular methods and see whether they are agreeing with each other, or say blood sugar by a pinprick on the bedside versus the lab sugar, there we are looking for agreement. So here we are using this. Let us take the same example. We have weight here, and you see the weight is a continuous variable and it's normally distributed. Cholesterol is a continuous variable and normally distributed. Triglyceride is continuous but skewed. So if you want to study the association of weight and cholesterol, that is weight and cholesterol, both of them are continuous variable, both of them are normally distributed. You see both are numer, more than 30, normal, one group, they are not related, they are related, and we use correlation, Pearson's correlation R. If it is more than 0.7, we know it is very good correlation. And here this is a data output which says the Pearson correlation. So we look at the correlation value and we look at the p-value. Sometimes you can get a very small correlation, 0.2, but a very strong p-value. That happens when we have very large data sets. And here we can look at the high positive correlation, high negative correlation, no correlation. So this can be represented by a scatter plot. Similarly, if you want to look at weight versus triglyceride, and I told you that triglyceride was a skewed distribution, so it's one is normal and the other is skewed. Even if one of them is skewed, you have to use non-parametric statistics, and here we use correlation Spearman-Rho. When we want to say, does increase in weight result in increase in triglyceride? Here, again, we can use linear regression when we are trying to show that change in one results in change in the other. So it is that equation which we used to learn in school, y is equal to mx plus c. And here again, does weight result in increase in triglyceride? Now you see how I have reworded, this is high triglyceride, that is more than 200. So I have made a continuous variable into a category. When I make it into a category and put this as an outcome measure, then it becomes logistic regression. So here the predictor variable is weight or obesity, and the outcome variable is triglyceride, which is more than 200. Similarly, we want to look at fatty liver present or absent. We want to see whether one radiologist agrees with the other. And here we use the kappa statistics to look for agreement. And when we want to see one lab triglyceride agrees with the other lab, then we use the Bland-Altman plot. So in summary, for the continuous variables, increase in weight is associated with increase in cholesterol, correlation Pearson if it is normally distributed, or we use Spearman if it is not normally distributed. Does increase in weight result in increase in triglyceride? We are saying that one thing is affecting the other. we use linear regression. When we are saying increase in weight results in hypertriglyceride or normal triglyceride, here it's again made it into a yes or a no situation, then it's a logistic regression. And when one radiologist is saying fatty liver, does it agree with the other? It is kappa statistics, kappa agreement. And does one lab triglyceride agrees with the other? It is Bland-Albert plot. Now we come to obese. Categorical variable versus continuous. This is very common. We have the obesity group, we have the overweight and the normal, and we have the actual triglyceride values. We want to study them. So if they are not related, that is the independent three groups, we are using student t-test. The equivalent for skewed is Mann-Whitney u-test. If they are related, that means pre-treatment and post-treatment values in the same person you want to study, then it is the paired t-test. And the equivalent of that is Wilcoxon sign rank test. If there are three groups, we use the ANOVA. And if there are again skewed distribution, we use the Kruskal values. So practically, I would suggest just take a print out of these slides and keep it somewhere. And whenever you have to apply, just see which category they come into. So the student t-test is very simple. Is that suppose we have the cholesterol level here on the x-axis and the number of people on the y-axis. This is the control group. This is the obese group. The obese group has higher mean values compared to the control group. So the student t-test is to determine whether the means of the two sets of data are significantly different from each other. So it is looking at the two different means, taking into consideration the standard deviation to say that these two populations are different. So the samples have come from different population. To say that thing, we use the t-test. So here in a real life situation, you see this is the control group. The means tend to overlap. And this has come from N1 sample. This has come from N2. So we are saying that they are coming from two different populations and there is some degree of overlap here. In contrast to the previous example where there was no overlap, this is a hypothetical situation. So here again, it's very easy to do it in SPSS. We are looking at cases and controls, that is obese versus non-obese and their vitamin D level. We use the independent t-test and we look at the test variable and you get this statistics. Now, this is where we need to interpret. Here you have 27 in the cases group and 24 in the cases and 27 in the control. In cases, the value of vitamin D was significantly lower, 28. Was 28 plus minus 9.7 versus 54 plus minus 18.3 in the control group. And here we have to look at the p-value which is below. And we look at the p-value and these p-values are significant. This is where we do. I won't have time to go here, but basically here it is also looking at the variances. And here if you see the variance, you see the standard deviation here is small, here it is fairly large. So we cannot assume that this variance is equal, and that is why we have to use the lower p-value. Equal variance is not assumed because the standard deviations are widely different. So this is how you represent it, mean levels of vitamin D in cases significantly lower than the controls, and you put your value and p-value. So it has 5 simple steps. You have a hypothesis with a pre-specified analysis plan. That means in your protocol itself, you should specify what kind of analysis you're planning. You can have mock tables in your protocol itself, empty tables. Then you organize your data in a spreadsheet and use it in a statistical program. Then you check the status of these 5 things. Is it single group, multiple groups? Is the data normally distributed or not? What is the size? Is it more than 30, less than 30? Is the variable a categorical variable or a numerical variable? And if it is a categorical variable, is it binary? That means just 2 or 3 things, or it is an ordinal variable? Or is it a number, and if it is a number, is it a continuous variable or is it a discrete variable? So discrete variable cannot have a decimal point, and we see whether it is related in some way or the other, and then we use some specialized test in related samples. Then we apply the test, we interpret it, and then we present it in text and graph. So do not torture the data until it confesses, because quite often people are so excited about p-value of 0.05 that it is important to just analyze and not go into various subgroups. And the ground rules are: have your pre-specified analysis plan, apply the appropriate tests which we have discussed, do not torture the data, and post-hoc analysis are all hypothesis generating. So the initial thing is hypothesis testing, which is You go by a pre-specified analysis plan. If you do not get that, then you say that we did post hoc analysis, which is hypothesis generating. Accordingly, in your discussion, you can tone down the importance of your study. And any subgroup analysis should be pre-specified. There's a very good study paper by Gordon Gayath on this subgroup analysis. I would advise you to read if you do a lot of subgroup analysis. And too many tests will increase the alpha error. Thank you.
Thank you, Dr. Datta. Can you take off the slides if I can request you for that?
Sure. I'll do stop share. Yeah.
Sure. Thank you. Thank you. That's a brilliant presentation. Very simple. I'm sure the students will learn quite a few things from this. Can I request Dr. Harshad and Dr. Madhumita to take up the Q&A session from here on?
Yeah, Dr. Reddy, there are a couple of questions, and one is quite interesting and pertains to the large country that's India. So this is from Prajna from Cuttack, and she says, India is a large country and it becomes difficult to cater to the huge bulk of patients in a government medical college and maintain data records properly. How do you tackle this problem? And I think after you answer, maybe I can answer and give my take on the whole question.
Yeah. So thanks, Harshad. So I guess when you have certain challenges, you have to ask yourselves, what kind of endpoint should I look at? Just hypothetically, if you want to see changes or trends in ALT, AST over time, that may not be a practical question, considering that the data, the records may not be complete. So one has to address some hard endpoints. What are events? Mortality, hospitalization, organ failure, say if you're looking at the cirrhotic population. If you're looking at drug-induced liver injury, rather than trends in transaminases or bilirubin, one has to really maybe just look at peak bilirubin and look at outcomes. So I think you'd have to really tailor your question to the challenges you have in your given area of obtaining data. I'd like to hear your thoughts, but we need to inculcate the culture. Somehow we need to really get the culture out. Hey, listen, it's a collaborative effort, so we need to partner. We cannot work in silos. And there are great communication tools now. You're doing Zoom. We have a fair number of these video conferences on multi-center studies. So I think somehow the culture has to change, and that's the only way you can get good data out. The power of a study is based on the number of patients you have from various parts of the country. That's the way I see it.
So can I just rephrase that question, and that would go to Dr. Harshad as well. So in a resource-limited setting, when we don't have an electronic database and people have to manually maintain data records, Dr. Harshad has created the Delhi registry. It's a work of over 20 years now. So how do people, for example, the student asking from Cuttack or in a peripheral center, what is the best way you would suggest to maintain a registry for future data review?
Right. So the best way, maybe Harshad should answer. Okay.
Yeah. I just wanted to one thing that struck me when Dr. Reddy said, I think it's the culture. I think we should we should inculcate this into the residents that come to us. It requires a tremendous amount of discipline, and we have. As a country, I think we have been a country of approximations. We don't sort of devote the same time discipline into maintaining records. But I think it is up to the mentor to inculcate this habit. And once you inculcate that habit, then I think it becomes much easier. And with regard to our Delhi registry, I think it took me a lot of time, effort, phone calls, etc., to talk to various investigators to enter the data properly. I think initially it's a little irritating, but after some time, the investigators who actually give you the data get used to your pestering. And to be very honest, one of the finest data I actually got was all from medical colleges. I got it from, for example, Sion Hospital. I got it from Cuttack Medical College, from New Delhi, and PGI Chandigarh, these are all government hospitals, and I think I got fantastic input from these institutions, perhaps because they have great mentors who have inculcated that habit in their residents. So it is possible. I know it's difficult in an Indian setting, but we can do just fantastic studies just by simple AST, ALT, or liver function test variables. We don't require sophisticated equipment or PCRs to come up with a great study.
So one other thing, Harshit, I mean, along the same lines, I mean, the industry provides a lot of support, and one area where, again, it's a cultural issue, is in the area of supporting databases and maintaining databases. So if you look at HSCC or a NASH target database, it's all supported by industry. All those companies that have an interest in NASH clinical trials, they're supporting it. When we had the HCV target database, it was all supported by industry, Gilead, BMS, AbbVie, and we were able to generate some good real-life data. So I think that's another area that one would perhaps consider working. And lastly, and talk about publications, I see so many. I believe for a DM there is a thesis requirement, but what happens is it stops at the thesis. I'm not sure why it's not taken to the publication level, and maybe there should be a change in the curriculum that unless someone really completes it as a publication, maybe they're not to be recognized. I don't know how you can change the culture, but it stops there. It's lots of nice work that's done, but it stops there. So again, something needs to be done there, I feel.
So a quick question as the segue to your point, sir. Do you think it is more difficult for students to now get published as it was 20 years ago? Because if you look at most publications, these are generally multi-centric trials with a large database registry. They are well funded. And when you're talking about a DM or an MD thesis, this is done in a very limited setting, and there are time constraints as well. What advice would you give to our Indian students as how to get published, how to convert their thesis into a paper publication?
Yeah. Obviously, this is challenging. It takes a time commitment, and you really have to ask the right question that has a chance of getting published. So it's obviously very challenging. Let me just give you an example. A medical resident at our place wanted to look at renal outcomes after liver transplantation by race ethnicity. So I said, okay, it'll take some time. Either you could, and it's been done with UNO's database. So I said, listen, let's take our entire database and go over case by case, and look at the evolution of renal function. It took the person about a year just to get that on 600 patients. So it takes time. So medical students should not expect a jackpot in a month's time. It's sort of a rotation on your service and say, I want to do something, and then disappear. So it can be done, but it has to be done carefully. And the key thing is also there has to be some mentorship in how to write a paper. I see some papers, there's like a storybook written. I mean, just I tell them focus. My simple mantra is, if you make 6 observations in a paper in your database, that's worth 2 papers. No paper should not have more than 2 to 3 key observations, and that is the way to look at it. Make it simple, and then obviously address a key point or key points.
So there are a couple of questions for Dr. Saurav Datta. So Dr. Jatin and Ramalingam have asked, why is there this risk difference of 18% that is taken?
I saw the whole chat, the Zoom group chat. There are quite a few who asked that question. The answer is I just plucked the number out of the air. So So the next question I'm sure will be, okay, then in that case, how do we decide what should be the desired effect size or the difference between two groups? And as I had mentioned in passing during the talk, there is no magic number. That it's not that a difference in one study can be simply transplanted onto another study and you can do it that way. So there are two things that influence how much that difference should be. One is the seriousness of the outcome that you are studying. So if it is death which you're studying as an outcome, say between oseltamivir and placebo, you would actually want to pick up even very small differences. So 18%, is outlandish actually. So please don't go with the impression that that's biologically desirable or plausible. You'll be looking for differences of maybe or even 5% difference in mortality between the two arms would be enough to change practice, because death is a big thing. If it's a less serious outcome, say something like duration of hospital stay or cost or something, you would then be willing to have bigger differences. That means you want to have bigger differences before you start changing your practice. Okay. The second thing that influences this difference is how much is your expected baseline rate. So supposing your baseline rate of mortality in a control arm for a particular disease, say severe coronavirus, is very high. It is already, say, something like 40 or 50%. Then you would be looking for a larger reduction. If your baseline rate itself is very small, say, you're dealing with hepatitis B or something, your baseline risk of dying is itself only about 5%, then you can't be looking for huge differences in risks. You'll be looking for small differences. So basically, it should be a difference that will compel you to change your clinical practice.
Okay, so sir, for a student, I think the most common question would be asked. This is for both Madam Dr. Usha Datta and you, Dr. Saurav Datta. How does a student determine, or what is the rule of thumb used to calculate the sample size for an observational study? How should they decide the sample size for a case control study and for an RCT? Can you just simplify it for people to understand in simple terms?
Usha, you want to take that question first? Oh, okay. Madhumita, who do you?
This is exactly what the student will come to you with. How I want, because what the guide frequently will tell the student is that, okay, let's work on portal vein thrombosis in cirrhosis. Yeah. And then they come to you and say, sir, how do I determine, the sample size that I need to do for my study? Or someone says, okay, let's give vitamin K in patients who have prolonged prothrombin time. And how do you calculate the sample sizes in a case control study? Yeah. So
all these situations that you're describing are all basically two group comparisons. There are two groups. There is a case and control, or there's an exposed and a non-exposed in a cohort study, or there's an intervention and a control arm in a randomized control trial. So the sample size calculation, the formula are actually the same because they're all two group comparisons. So if you're dealing with a binary outcome, means a categorical variable that has yes or no, like death or sequelae or chronicity or whatever, some binary outcome, there are 4 ingredients that you require to plug into the sample size calculation. 2 are fixed, the alpha error and the beta error. By convention, you can't change them. I mean, it'll require a lot of guts for someone to start using a different alpha and a beta error. And those are, as I said, 5% and by convention 20%. But these days, a lot of people are insisting on beta errors of 10% as well. The 2 other ingredients you require are, from existing data in your unit, what is the baseline rate in the comparison arm in any of these studies? So that means, what is the baseline rate in the non-intervention arm? When you don't intervene, what happens? Or if it's a cohort study in the non-exposed arm, what is usually the rate of the disease? Or in a case control study, what is the rate of exposure in the non-diseased people? And then from, if literature is available, any preliminary literature, you try to find out what has been the magnitude of effect that other people have reported so far. So that is the fourth ingredient, the magnitude of the effect. So in a randomized controlled trial, it will be the difference in the rates between the intervention and the control arm. In a cohort study, it will be the difference in the risk of exposure, risk of the outcome between the exposed and the non-exposed arm. And a case control study, it will be a difference in the risk of exposure between the diseased and the non-diseased arm. So once you get this from published literature, you plug it in, you find out the sample size, and then very importantly, you see whether it is feasible. One of the most important things about a study is feasibility. In fact, there are these finer criteria for deciding whether you should do a study or not, and the F in those finer criteria stands for feasibility. Unfortunately, a lot of times, MD and DM theses are launched without them being feasible. And then you end up having a small sample size where it's inconclusive. And that's rather disappointing. So that's my take on it.
In fact, Madhumita, we have a separate session on sample size, how to calculate a sample size. It's coming up in next series. So don't spill the beans here. I'll request you to go on to the next question.
Okay. I think Dr. Usha Datta had an excellent presentation. I mean, I think it was so abundantly clear to all who were present. A question to her would be, when a student is preparing a protocol, how do they frame their statistical analysis? What are the pointers that you would give to the student? One, in terms of sample size calculation, of course, and what statistical methods that actually have to be applied, and what do review boards actually look for when they determine whether a certain protocol has to be funded or not. So how do you write a good quality protocol to ensure you get funding? This is for Dr. Usha Datta.
Kindly unmute yourself. You need to unmute yourself.
Yeah, thanks, Madhumita. I think it's a very essential question and quite often asked question by our students. And even when we write research protocols, many people do not give importance to these two paragraphs. The two key paragraphs are, how do you plan your statistical analysis and what is your sample size? Sample size, as Manav said, that's going to get discussed, but there are various statistical softwares available on the net. In today's day, you don't have to do any maths. The computer does the maths. But the more important thing for us to understand is the principle behind the maths. That is what is. So I would suggest anybody who wants to pursue research as a career should attend a series of research-based, research methodology workshops to understand it to the core, so that you can then apply the principles. Coming back to the paragraph usually gets worded in a standard way that we will enter the data into an Excel format and that will be taken on to a statistical program, and all the data will be categorized as categorical or continuous, and then all continuous data will be analyzed whether it is normally distributed or not. So assessing normality, we will be using PP plot or QQ plot, and one of the statistical tests like Shapiro-Wilk test or Kolmogorov-Smirnov. Based on that, we will choose our statistical analysis. We will be, for categorical data, we'll be using chi-square test or Fisher exact test if the expected cell size is less than 5. So these are standard ways of just wording it. If anybody needs, I can give a standard paragraph of how to write it. And then comes the key part. So this is standard for everything. Then the key part comes is, are you going to have 3 groups? Then you say, okay, I will be using ANOVA. If you're going to have 2 groups and you expect it to be normally distributed, we use student t-test or Mann-Whitney u-test. And then you decide whether you're going to actually look at regression. Are you going to be, your outcome, is it going to be triglyceride level, or is it going to be high triglyceride versus low triglyceride? If it is a triglyceride level, you will put in a few lines about linear regression. If it is high versus low, you put in a set of logistic regression. Then you will then decide, actually only when you do, you will decide whether it's stepwise forward or backward or enter method, whatever method you will be using. So that can come when you actually make your final paper. At the level of protocol, you just need to say how you're going to describe your variables, how are you going to choose your common statistical test, and whether you're going to do a multivariate regression or not. And sample size is a separate paragraph. As Dr. Saurabh was saying, we specify the beta error, the alpha error, and then I think the next session will tell us about that more, so I won't dwell into that. But there are two such standard paragraphs which have to be carefully worded, as if a person who has knowledge of biostats has worded it. So that is important.
Madhumati, I had a point I guess I want to raise. So you're a mentor, right? So the student comes and says, I want to design a randomized trial. Don't you think the first step is to generate some pilot data before you even design a randomized trial? And I have a question for Dr. Datta. So you gave an example of a 100 patient study. So how do you decide to pick up 100 patients? I mean, without any knowledge of what a intervention might do in a given cohort. So if I was advising a mentee, I'd say first, let's see if this drug has any kind of effect in this entity before you design a randomized controlled trial. I think we need to take some baby steps before we just say, all right, let's hit the jackpot. So I just want to get, I mean, it's nice to have lofty ideas, but we want to start simple. So I'd like to hear thoughts on this provocative kind of issue that I raised.
No, I understand. I had kept this data set as a very simple data set. This is a hypothetical data set so that I can, convey the simple numerical issues. I didn't go into decimals and larger data sets. So this data set was completely an hypothetical data set just to tell people, if you take 100, 100, 100 and you get these values, how will you do a statistical analysis? And obviously, if you have to do a study, you have to take the standard principles of sample size calculation, look at what is there in published literature, do your own pilot, and on that basis, you choose your sample size.
It's already 8:26 and we are running short of time. So can I request Dr. Thuluwat for a word, and then I'll request Kaushal to sum up the things.
I think I enjoyed the talk and I learned a lot from all three of you. I hope our trainees can watch this recorded few times and learn from this, because some of the simple statistical methods many of our residents do not understand, and they think it is too complex. But if you take step by step, as two of our speakers suggested, they could learn it pretty fast, and especially SPSS. It's a window-based program. Most people can do most statistical methods by SPSS. They don't need to write a program like SAS and others. So I think, thank you very much for this wonderful talks. Raj, as usual, is one of the very productive publishers, and he has done a lot of experience mentoring. I think it was a wonderful session. Thank you.
Over to Kaushal, please.
So I think all of us agree that the talks were fantastic, and I learned a lot of things, and I'm sure the students and fellows would immensely benefit all of them. And I'm already receiving feedback on my WhatsApp telling me that they were very lucid talks, and people would want to go back and see the videos. And just to bring it up, I was told by the organizers, the Maisha group, that every day there have been about 15 to 20 looks or relooks at the videos of the previous presentations. So that's very encouraging for this series. Thank you so much, everyone. And in the end, I would also want to thank Sun Pharmaceuticals, who have been the educational partners for this particular webinar. And don't forget to log in again next week, same time. It's all about data. As everyone says, data is the king. So it's data, data, data. So the 3 talks on how to set up a prospective database, how to best use databases for research, and how to best use population and insurance claim databases for research. And the speakers are very prominent hepatologists, Dr. Jasmohan Bajaj, Professor Thuluwat himself, and Dr. George Enau. So thank you very much, and please stay safe. Let's meet next week again. Thank you.
Thank you.
Thank you all.